Right, okay. So good evening, everyone. Thank you for joining today's webinar organized by the CEE and HKIE Civil Division. The topic today will be on risk assessment strategies for the environmental impact of dredging and mining in coastal areas by our Professor Alessandro Stocchino, who has joined the CEE in August 2020 as an associate professor. So without further ado, please welcome Professor.
Thank you. Thank you so much. Well, I'm very excited to be here today. It's my second time that I'm doing this online seminar together my department and HKAI. Today, I will try to introduce what I have been doing in the last 2-3 years together in collaboration with my student, He Chang, and other two colleagues, Professor In, which is a specialist in geotechnical studies, and Professor Onyx Wei. But before entering into the topic of today, let me allow me to introduce our department, the Civil and Engineering Department. Well, it is one of the world-renowned department in civil engineering, and this is testified by a large number of recognition that we are collecting globally, from the ranking of the university to the ranking of the a lot of colleagues are in the top 2% scientists of the Stanford University world ranking. So we have been very successful in collecting a lot of very important funding of research proposal of the largest scale that we have here in Hong Kong, funded by the government agency, the RGC, and other agency. For example, these are some example of flagship projects that we have been awarded starting from 2017 in the theme-based research scheme. These are other examples of very important project funding scheme, the Grid Tech Fund of the EPD, and the Lantau Conservation Fund, and the RGC Collaborative Research Funding. A lot of topics are really related to the civil engineering, geotechnical engineering, and coastal engineering, together with the environmental and air pollution topics. In our department also, we deliver different programs, undergrad programs in civil engineering and environmental engineering and sustainable development. We had 2 Master of Science courses in civil engineering and environmental management and engineering, plus Master of Philosophy and PhD programs. So we have a list of really outstanding alumni, as you can see from this slide. So it was an honor for us to have this alumni in our department. And in terms of facility, we have a very large number of laboratories dedicated to all branches of civil and hydraulic and environmental engineering. And currently, we have also a research center in Shenzhen. So if you want to have more details about our activities, you can follow on the website, on our social media channels. Now, going to our topic, this is pretty much the program of today. I will try to provide some background and context why dredging is so fundamental for coastal engineering in general, some basic concept of dredging operation and the standard risk assessment approach. And then I will introduce what we are proposing in these years. We have been trying to improve the risk assessment approach. And then I will give you, I will immediately apply this approach to a pilot case here in Hong Kong. And then finally, the point 4 and 5 is how we can consider and extend our approach also to take into account the fact that the sediment many times is polluted, or what are the impact on some species, mammals or other species that are protected in our seas. So in terms of background, I want immediately to concentrate to what we know better. So it's the Pearl River Estuary and Hong Kong and GBA in general. As you are well aware, the Pearl River Estuary is one of the largest in the world, and probably and for sure it's the largest in China. Is the Great Bay area in general is very active with an incredible GDP and is the location of really large megacities. What happened in the past 50 years? You can see from this plot what happened in the Pearl River estuary and in the GBA in general, where a lot of land was reclaimed. You see the yellow, orange, and red, and a lot of sand minings was done in the Pearl River estuary, and to allow the navigation, different channels are regularly maintained during dredging operations. So this is immediately to understand the impact that we have in terms of land reclamation, dredging, and sand mining operation, even locally. Worldwide, of course, it's similar, but we will make a comparison in a few minutes. So these are other pictures that show how the land reclamation that is based mainly on dredging operation has been visualized in this starting from the 70s till 2017, and so we noticed that we had a large increase in lands. So going to Hong Kong, on the left side, you see the green area has been all reclaimed land since the end of the 19th century. And Hong Kong, as you know, has been discussing in the last years also to do this new development in terms of artificial islands. So actually, we need to make a very short digression in terms of what we'll be expecting in the future. So as you know, we are under climate change evolution, so there are a lot of estimates in terms of sea level rise, and this is a parameter that we better know depending on the scenarios. The last assessment report at number 6 actually concluded that our projections are even slightly worse than the previous one. In terms of sea level rise, for example, many databases are available, like this one from NASA, where you have the historical data, and so you can understand the trend. If we go down and zoom in our area, you see that the projection anyway is an increased sea level rise. So you have other data sets where you can have the full projection depending on the scenarios. And looking in our cases, we expect, depending on the scenario, the sea level rise that can be also about 0.5, 0.7, and even 1 meter in the worst scenarios. This is an example what we should expect in case we have a 0.7 meter increase of sea level. So the blue areas, as you can see, will be flooded. Well, this is globally a trend. So this study actually reported all the reclaimed land worldwide, and noticed that in the Southeast Asia, pretty much occupied the 90% of the worldwide reclaimed area. Problem is that in the future, we expect that most of these coastal cities will be under flooding just to the sea level rise. So here comes some example of what we can do. For example, this is taken from Singapore, where they are planning actually to move forward the coastline with the aim to protect the city. While this kind of operation, the basic work will be, of course, coastal dredging. So what is coastal dredging? Well, dredging can be divided in several classes. We have the maintenance dredging, which is the standard operation, for example, in navigational channels and for harbors and ports, because the natural process of deposition, sand deposition, is worldwide and we cannot stop it. So maintenance dredging is to maintain a correct water levels for navigation. What we call environmental dredging instead is, for example, as environmental purposes. So sometimes the sediments are polluted, so with dredging, you tend to remove the sediment from the coastlines. So the main operation, 3 essential elements of dredging can be listed: excavation, transport, and disposal. And This is part of the dredging design. So you need to design and understand what are the volume that you need to excavate, the transportation routes that you need to do, and the disposal of the sediment. The dredging method, well, depends on I will show you very quickly a lot of dredgers that we have available. Well, you need to take into consideration several characteristics. For example, the dredger can be more or less sensitive to wave and currents. They require a minimum water depth. They require a minimum space for maneuvering. And then, depending on the soil, you have to choose the proper dredge, and depending on the volume, you need again to decide what is the proper production rate. That depends on the dredger. Here are some examples. We can divide it in mechanical dredgers. These are examples of dredging by crane or backhoe. Is usually less sensitive to waves and currents, but the production range usually is very small. These are example of hydraulic dredger, like the cutter dredger, where you can reach very high production and achieving relatively accurate sea level leveling at the end. And then these are hopper dredgers, other example of hydraulic dredgers, and this is another small scale mechanical dredger, which is the ladder bucket dredger. What is the point? And this is example how you dump the sediment where in the location that you design for the dumping. So you can have a direct dumping from the barge of a spray, like in this picture over in the right bottom corner. So in the dumping, which is a pretty sensitive operation in terms of also, as we will see, in terms of environmental impact, can be done directly on land in case of land reclamation or in open water. And it can be done very close to the dredging site or even very far from the dredging site. So what are the main problems that we can cause during the dredging operation? We are definitely resuspending a lot of fine sediments, and I will define later what is the fine sediment that is sensitive for dredging. So you generate sediment plumes that can have an impact on the aquatic environment. For example, just increasing the concentration of sediment, you block the sunlight. So for fish and other species or even seagrass can be an environmental problem. Another associated problem is that sometimes the sediment carry contaminants. So in this plume of sediments, actually you are also transporting contaminants. So you have the environmental impact is usually associated with the sediment jet formation. And the sediment jet can be a single point spill, for example, as it's a simple mud overflow. As you can see here, you have a generation of mud clouds, or even a semi-continuous, like, for example, when you have a free fall spraying of sand or mud into the water, like in this picture here. So let's enter into some more details. What we care especially is the so-called mud fraction or the fine sediment. So this is a typical example. This is taken here in the Hong Kong waters. It's a sample of sediment. You can see in this plot the grain size distribution. What is delicate in the environmental impact and the jet evolution is considering the sediment with a size less than 64, 65 microns. So this part of the curve, because this has the ability to be carried over very long distance and for very long times in the dynamics of the evolution of these sediment plumes. Okay, how about the plumes? Of course, technically speaking, the process is extremely complicated because the simple release, like in this picture here from a barge, actually has a different, several dynamics involved that covers different time scale, as you can see here, and different length scales. So at the very beginning, As soon as we release from the barge and dump the sediment, you have a very convective stage, highly turbulent, and it lasts, the time scale is seconds. Then there is a stage where we call the near field, number 3 in this picture, and P in this time scale here. Well, still the plume is very active, so it's the buoyant forces that are basically driving the process. But then you have a far field evolution, so the plume can reach very long distance depending on the waves currents and the other source of currents, like wind currents or any type of tidal currents, for example. So usually what we care in our assessment is not much about the near field, but rather on the far field. How we tackle this problem? Okay, in the past, there was several even analytical approaches where you can estimate roughly the diffusion of this initial concentration. But nowadays, where the numerical simulation, hydrodynamic and sediment transport simulation are commonly used, even in the, of course, also in the engineering practice, while the most suitable approach is to use the so-called advection diffusion equation here that you can see, where C is the concentration of our sediment, Ws is the settling velocity, because of course the sediment is heavier than water, so sooner or later will tend to settle, but then it's a balance, of course, with the local current. So this fully three-dimensional equation allow us to provide an estimate, like this is an example of plume evolution. What is important, I underline already here, that everything must be computed in terms of concentration when the hydrodynamic characteristic of our currents in our site is known. So U is the three-dimensional velocities. Again, I remind you that this equation is strictly valid when we consider the far field, okay? So the long time scale and large spatial scales. Well, how can we solve this equation numerically? Well, there are a lot of hydrodynamic and sediment transport solvers nowadays available. Some are open sources like Delft3D as well, FECOM, Schism, then Mike from DHI. So there are tools that nowadays are very common in the every consultancy company. Then our equation requires an initial condition. What is the initial condition? So I have to define what is the amount of sediment, for example, that during the dredging and dumping, I expect that will be released in the far field. So there are several empirical formulations of this. In this slide, actually, I summarize the entire process. I said, oh, sorry. I want to reduce this. No, okay. I'm referring to this paper published in the Journal of Environmental Management, which is relatively recent, 2015. It's a fantastic guide to assess this first stage of a dredging risk assessment. So the idea is, depending on I start from the knowledge of my sediments. I know the volume that I need to move in the dredging operation and in the dumping operation. I know of course, in the design, I decided the type of dredgers, the trailing suction hopper, cutter suction, there are several ones. I know for each dredger pretty much the expected amount of sediment, fine sediment, so less than 63 microns, will be released. I know the duty cycle. Basically, this is an example for the trailing suction hopper hedge, the duty cycle of my dredging operation, and I need to design also the working timetable. So imagine that from 1 to 15, this is a window of 15 days. I can decide different working modes. So one day I will do dredging and dumping, and then I stop, or working mode two, for example, is I do dredging and dumping day 1, 3, and 5, and so forth. So this is part of the design, but the output of this will be the initial condition for my numerical model in terms of sediment fluxes in every point of my domain, okay? So using as a example these hydraulic dredgers, okay, I know that the who is generating a plume of sediment is exactly at the dredger, so the spill caused by the drag head at the bottom. I have also an overflow from the barge, and then the number 3 is usually not included because it's too complicated, which is the risk suspension due to the propeller, okay? So this is, for every type of dredger, I have this type of knowledge. And then this is an example of what is a duty cycle for dredging is. So time 0 represents the beginning. So you see that the amount of fine sediment in the hopper will increase. Then I have my barge, which is filled. And then I will sail between time 2 and time 3 on the dumping position. And between time 3 and 4, I will dump. And then from 4 to 5, I will sail back to my dredging operation. So this is usually in the dredging design. Then you have, of course, this time 0, 1, 2, 3, 4, 5 defined in hours, for example. Well, then from the total volume that I have to be dredged, the sediment information, so the grain size curve, I can evaluate the total mass in terms of dry solids in kilogram. And then I can decide, with some empirical formulation, again presented in this very interesting paper, I produce this time of sediment fluxing timelines, okay? That will be provided point by point to my numerical model. Of course, in dredging, you can also have some measure for using turbidity during the dredging operation, like curtains and booms. Usually in the risk assessment analysis based on numerical simulation, this part is not easy to take into account. So it's not easy to model the presence of these mitigating measures. Somehow, this means that your risk assessment take into account the maximum risk that you can have during your dredging operation. Okay, what is the concept of risk then? Because this is fundamental to go into the details of the standard approaches and what we are suggesting as a new approaches. Well, usually risk is a superposition of the hazards. So what is generating hazard in our case is the sediment concentration, a very increased sediment concentration, so the sediment plume. Well, the hazard then must be superimposed to the vulnerability and to the exposure. So vulnerability means that in your site where you want to operate in your with your dredging operation, of course, you need to be aware of some coastal protected areas, aquaculture sites, or sites with very high values from a socioeconomical point of view, like beaches, for example. The exposure means how the vulnerable area are exposed to the hazard. When you superimpose this, you get the risk. So what are the risk assessment approach? Well, there are many, of course, but one of the latest that has been, especially in Europe, kind of reach a kind of consensus is, well, summarized in this scheme. Basically, you have on the left box, actually, the 3 main parts of the computation of the hazard, which means you need to, of course, know all the data of your site, the oceanographic and meteomarine condition, like density, water levels, wind, waves, and then you generate the hydrodynamic. Using hydrodynamic modeling, you can generate a correct evaluation of the hydrodynamic condition for your dredging. Then you have to, of course, define your dredging source. So the dredge rate, the dredge spills, the source geometry, what type of dredging duty cycle you are using. And of course, you need to then coupling this and produce some sediment transport modeling to evaluate the dynamics of the sediments. Okay. In this year, we have thought a lot about this, and one of the key aspects and limitation of this approach is at the very beginning. So how we can define the typical hydrodynamic condition? Because what we need to do when you do an hydrodynamic condition, you usually need to know the wind, the tides, river inputs if you have, salinity and temperature, of course. But what is typical? So if you go through the paper where the author presented this, summarized this risk assessment, they usually define very few hydrodynamic condition. So they call typical, for example, the average condition. So you have, I don't know, wind time signals of 20 years, you take the average, that's the condition. Or I have seen also in this part of the world using typical wet and dry season. So the simulation then covers very short time period on what is called the typical wet and dry. So what is the main problem here? That is the hydrodynamic that you are reproducing has a very low statistical significance. And if the hydrodynamic has a low statistical significance, the risk assessment that you are producing has a low statistical significance. So how we try to improve this? Well, this is the workflow, and I will try to enter in a little bit more details of the methods, the approach that we are suggesting. Basically, we are not changing anything in terms of the numerical approach. Of course, hydrodynamic modeling and sediment transport modeling are the key steps, okay? But the idea is that we try to make the choice of what are the typical conditions in the more with the more statistical meaning. So the core is here. So because the first block is the dredging plume, of course, and you can define n certain number of dredging scenario and which is typical. So I can test mechanical dredging, hydraulic dredging, different location of dredging, different duty cycle of dredging, and different production, for example, of dredging. So nothing new here. The core of the approach is in these red blocks where we rely on some very simple machine learning techniques to decide what are the typical meta-ocean scenarios. So what are the typical wind field, tidal elevation, air pressure in my site where I have to design the dredging operation. Then you go for the sediment transport numerical model. So at the very end, you will have, I will show you later, hundreds of scenarios analyzed. So the hazard that you are computing has a very highly statistical significance. Then again, we don't change anything in terms of vulnerability. We can take into account environmental indexes, socioeconomic indexes to build up the vulnerability. And then again, the risk is the multiplication, so the superposition of hazard and vulnerability. So this is the step-by-step of what we are proposing. So first of all, collect the meteorological and ocean data of the specific site. This is easy. Many data sets are available online, and you can download everything in terms of wind field, tidal levels, salinity, temperature, over even decades. Okay, some European data set, some US data set like NOAA has even 70 years of recordings. Then using these techniques that I will show you later, next slide, you generate a sufficiently large number of forcing conditions for your hydrodynamic simulation. You run the hydrodynamic simulation, and for every hydrodynamic simulation, you test different operational dredging conditions. And you ended up with an estimate of the hazard and the associated probability of occurrence. Then you estimate the vulnerability, and then you end up with the risk evaluation as a product of hazard times vulnerability. Oh, sorry. I don't know. I went to the, okay. So what is this, the core of this? Well, we use what is called k-means clustering, which is pretty simple techniques that, starting from your data set, again, from ERA 5, for example, a data set of wind, river inputs, tides, well, automatically the k-means recognize. Second operation is to define what is the duration of your numerical simulation that you want to do. In our test case, we tested 15 days and 30 days. Why? Because the evolution of a sediment plumes actually can last for days and not for months of years, of course. So the time scale of your process must be around a few weeks. So you define a time frame of few weeks, you run the k-means clustering, and the k-means automatically associate, divide in different clusters. This is just a sketch where for every point you have a set of wind, pressure, tides, all the forcing that you have to use for your hydrodynamic computation. This is an example here in Hong Kong, okay, just to show you how complex is our local dynamics. So that's why it's very difficult to define a typical condition here in Hong Kong. That's why we are suggesting to do this analysis. We ended up with simulating 100 2 weeks hydrodynamic scenarios. Then we need to define the hazard. So how can we define the hazard? This is again pretty standard. Imagine to have this. This is an example of suspended sediment concentration signal in one point in your domain. Of course, you have 0. Then you can have peaks of the SSC signal in a single node. Then you should decide some threshold. Well, the threshold is usually decided by the local government. So I cannot provide you an example. Here, EPD decides something. If I apply this method in Europe or in US, I have different threshold. But what we call pollution event is when our SSC exceeds this threshold, and for how long. Then in our work, we have, I don't want to enter into much details, but we suggested 5 ways of defining hazard. So the most important is probably the last one, the significance, that tells you, following this table, in a single point in your domain, assess a different value of significance depending on how much you exceed the threshold. So 30% more, 100%, 150, or more than 200%, and for how long? So because you might have an event where your SSE is very high, but then lasts very short time. So environmentally, that represents a not so hazardous event. And then we decided the dredging operation. We tested 3 modes of operations. So at the end, we had M hydrodynamic scenarios, 100 in our case, N dredging scenarios that were different dredgers, mechanical, hydraulic, different working modes. So we ended up with hundreds of simulation, and the hazard is then defined for the index that you want to consider, I, multiplied by the probability of the single hydrodynamic scenarios. This, differently from the standard approach, actually keep considering the probability of occurrence of this scenario that you are testing. Okay, so what this is just a final scheme. You have your hydrodynamic simulation, you do the sediment transport simulation. Here you have the example of a dynamic of a plume. Of course, here in the Pearl River, everything is driven mostly by the tidal current. So you see that this plume is going back and forth inside the Pearl River. And then for every scenario, for the total of these hundreds of scenarios, you produce an hazard evaluation. And in a map like this is the significance. So you can see where you have a distribution in space of the hazard. So then why is useful this approach? Because you can compare different working modes. HM means hydraulic dredging, MM means mechanical dredging, and these A, B, and C are the different working modes. So you can compare for the single dredger different working modes, or you can, for a single working modes, the impact of the hydraulic dredger or mechanical dredgers. Then we define vulnerability. This is the most subjective part, of course, and depends. For example, we based on the marine protected areas and on the beach and fishery, so some socio-economical indexes. When you couple this information, you ended up with the comparison of different working mode in terms of risk. So these are now plot of the risk. Risk 1 is the maximum because we tend to normalize this index between 0 and 1. So, and again, you can compare among different working modes, comparing different dredgers. But then we try to, the amount of information can be overwhelming because you have a lot of maps, okay? So we also propose some synthetic risk plots. One is to use a box plot. You probably are aware what is a box plot. Provided an ensemble of numbers, actually the box plot, which is represented here, usually it's called box because you have a rectangle and then these whiskers. And the rectangle usually is bounded by the lower quartile, quartile number 1. So the basically is the 25th percentile. Then you have the median, Q2 and Q3, and the whiskers are containing actually 25% more than the third quartile, and the minimum is 25% of the quartile number 1. So what is the idea? I took, for example, this map here. This means that in your area of interest, you have a distribution of numbers between 0 and 1. We never we cut it at 0.7, but it reached 1. And with this number, you produce a box plot. The second idea is very intuitive. As you know, you are for sure well aware what is the windrows. A windrows, which is exactly this one, usually is a synthetic representation of the wind direction and the wind intensity in terms of, and the percentage are the percentage of occurrence. So we said, why we don't do the same? So we take for a single scenario, the same direction of the winds, but instead of using the wind speed, we use the risk. So why is useful this? Because immediately for your design, you have immediately the idea what are the most risky conditions in terms of wind. So when you have this already prepared and you have the dredging operation planned and you have the forecast of a very strong wind, for example, from a direction where your risk growth is suggesting that you have the highest risk, you are already aware of of these conditions. So these are examples of what we have done. HM is the hydraulic dredger, MM is the mechanical dredger. For example, these are the box plot, risk box plot, comparing working load of 1 day, 3 days, and 6 days. Same for hydraulic and mechanical. What was interesting is actually if you increase the duty cycle from 1 day only up to 6 days of working load, actually your average risk, so average is the red line, is the median risk, actually increased less than linear. Again, this is a useful tool to understand the your duty cycle choices. So how many dredging working days of dredging you want to do in a specific site. Well, intuitively, a lot of people think that increasing from 1 to 6, the risk can be actually 6 times higher. Indeed, the results suggest of this analysis that some it's site specific, of course, but the risk can be less than linear. So this is a good guidelines for the engineers to design a better dredging operation. And these are example of roses, again, where you see that the direction are always the same because the direction are given by the wind direction. But indeed, the colors are the average, the cumulative risk for every direction. What does it tell you this? For example, let's take a case of the first one, where you have a higher percentage of risk for the when you have the wind that are coming from the sector northeast north, okay, and a very high risk also when it's coming from east southeast. So this could be a guide in your day-by-day operation when you are actually controlling, designing and monitoring a dredging operation. So very quickly, I want to introduce this. What if the sediment carries some pollutants? Well, for example, we did an example here in the Great Bay. We have a very high concentration of a very dangerous and noxious new pollutant, which are liquid crystal monomers. So we started from these papers published where you have the concentration of this, and they found this concentration attached to the sediment. So how we can take into consideration the risk, the secondary risk given by the polluted sediment? Okay, we used our risk assessment. Pretty much is very similar in terms of dredging scenarios, hydrodynamic conditions. So you ended up again with hundreds of suspended sediment concentration patterns. But then the definition of risk is taken for this specific, like environmental chemistry do. The risk is the quotient risk, which is provided, risk quotient, sorry, RQ, which is provided specifically for every pollutant. So in this case, just the presence of this polluted sediment is a risk. So we didn't enter into the vulnerability analysis. If you do this, of course, we tested, for example, different location of dredging around Lantau Island and different dumping conditions. And we ended up, again, with some nice evaluation of the potential secondary pollution risk due to the fact that you are dredging polluted sediments, okay, that sometimes happen. While we use this LCD as a prototype for pollution, you can do with PFAS or any type of polluted substances. Final, and we also care about to understand the impact, for example, of some protected species. For example, in our Great Bay Area, the Chinese white dolphin is a protected species. Anyway, we think that dredging operation, of course, should go on because our fundamental operation in coastal engineering, but we can understand what are the possible impact. So in this case, we modified what is the vulnerability of our analysis using the map where the Chinese white dolphins have been observed. So again, having the hazard evaluation, the new vulnerability, and you superimpose, you ended up with this risk map. Of course, they are very high where you have the intersection between the hazard and the most probable location where you can observe the white dolphins, because they have their typical environment where they actually live or they go for breeding. And again, you can also produce similarly these risk crosses, and this again can guide you in specific moment of the year, for example, where you have a higher concentration of observation of dolphins, where are the most risky wind condition in terms of sediment concentration overlap with the dolphin's habitat. So just reaching some conclusion, our proposed approach actually overcomes one of the main limitations of the standard risk assessment, because we more objectively define what are the typical hydrodynamic conditions for a certain dredging site. So the risk here is evaluated over hundreds of possible scenarios, leading to a more comprehensive understanding on the environmental impact and what are the probability of this risk associated with the risk. And then risk box plots or risk roses could be a very synthetic representation of the risk. We demonstrated that also the method can include very easily other environmental risks, like polluted sediment or impact on different biota. In this slide, I also listed some of the references that I used for this presentation. So thank you so much. I hope that in these 45 minutes, I hope that I gave you some ideas, and I would like that you bring some ideas in your day-by-day activity, of course. You have all my references. If some of you, of course, now I'm open to a Q&A session, but if some of you wants more details on this analysis, you can always reach me by email. Thank you so much.
Thank you very much, Professor. So now we will be taking in question. Oh, so we have one question now on the floor. So Professor, there's a question for risk assessment. Can we use a similar approach to predict the risk potential on coral species? Are there any limitation in assessing risk on marine animal or marine ecosystem? Cost to interaction is quite dynamic.
Okay, the answer is definitely yes. Trying to understand the impact on other sensitive coastal areas or coral colonies, for example, and species, of course, is possible, and it enters into the evaluation of the vulnerability. We show that for the vulnerability, we use different environmental and socioeconomic indexes. Then we switch to considering where the mammals like dolphins have their habits. We can similarly do where we have corals. So again, overlapping hazard and a specific vulnerability for corals, we can end up with a risk assessment for this case. Hope I have answered.
Thank you. Are there any more questions? You can either type in the chat box or unmute your microphone. Both okay.
In case I'm available also after the meeting, you can send me email and I can share with you some material.
That's right. I guess there are no further questions, but if you do, as mentioned by Professor, you can please feel free to email him. So in that case, I'm gonna switch off the presentation, and thank you very much again, Professor Stocchino.
Thank you. Thank you,
Thank
everybody.
you.
Thank you for attending.
Thank you.
Bye-bye. Bye-bye.
Bye-bye.